In this class we want to talk about trend lines and in particular pick out one type, that of exponential smoothing. Now I realize it sounds horrific, it sounds difficult and so on, but in fact it's quite a straight process and I'm going to step you through it quite simply to see how trend lines work, to see what they do and how they can improve our understanding of data sets. So exponential smoothing, we can start with an expression like this. It's at the bottom of the screen. Just put the cursor on. Here we've got our expression for exponential smoothing in this particular case. So we've got a time period, t plus 1. That means it could be today. T plus 1 equals today. So when I see t here, it means yesterday. T plus 1 could be this year, and t is the previous year because it's one less. T plus 1, t. T is less than t plus 1. So what I've got here is a forecast figure in time t. So that's the forecasted figure. And here is the forecasted figure for the next time period. And that's equal to the actual figure in this time period, the actual one, times some constant, alpha, some number, 0.6, 0.2, whatever it is. And over here we have 1 minus alpha. So if that's 0.2, this would be 0.8. 1 minus 0.2 is 0.8. And here's our ft, which is the forecast in the present time period. So that's in the next time period, let's say. That's the present time period. That's the present time period. That's one time period ahead, current, and current. This alpha here is just a fraction of 1. So it could be 0.2, 0.9, 0.3, whatever. And here it's 1 minus alpha, so if that's 0.3, that's 0.7. 1 minus 0.3. So the formula is actually very, very straightforward, very simple. And we're going to use this formula to work out our trend line. Let's say alpha is 0.3, just to get the ball rolling. I just made it up. So providing it's less than 1, you can start anywhere. So I'll start with 0.3. Now we'll have our sales and months. So these are 10 months, and here are the sales figures for the 10 months. So this is our data set. This is what we're going to analyze to see what trend is in here. Now we're going to smooth it using this formula. Now when we apply it, it's actually quite straightforward. Let's say we take the first one. Well, the first one is just the first one because we don't have anything before it. So that is that. Now this one here, if we look at the formula up here, we've got C15. I've put in little dollar signs here to anchor it. When you have a dollar sign like that in Excel, it means that cell is fixed. I tend to fix things. Anyway, so C15. So C15 is here. There's C and there's 15. So C15 is 0.3 times C4. C4. So we have this times this. We have alpha times the actual in the previous time period. We're trying to calculate this one, so we're saying the actual in the previous time period times 0.3 plus 1 minus 0.3. 1 minus 0.3. So 1 minus 0.3 times D4. D4. So it's the forecasted figure in the previous time period times 1 minus alpha. Now just drag it down. Just drag this one down and you get these figures here. Now you can look at any one of those. It's C15, that's fixed, times C9, that's the actual in the previous time period, times alpha, plus 1 minus alpha times the forecasted in the previous time period. So we get this set of figures here. So these are our actual sales, and this is what the trend is suggesting, that the figures that underlies the figures. This is the trend line. And we can test to see how good it is by using something called the mean squared error, MSE. All this does is you subtract the trend from the actual. So if you subtract 111 from 110, you get minus 1. Well, square it. Square it to get rid of the minus sign. So minus 1 times minus 1 is 1. This one here is 23.3, I think it is. Square it, you get that. This one here is minus 0.44, I think. I have to work it out properly. But minus 0.4, it's certainly a minus figure. So when you square it, you get that number. And so on. So now when you work out the average of these, and you can do that on the computer, on Excel, there's the average, just E4 to 13, E4 to E13. When you take the average, you find it's 59.98. Now if we played with the alpha, we get different figures here because we've changed into formula. So if I change that to, let's say 0.2, oops, it's 0.2, you see it's changed to 60. And what I want here is I want the smallest variation. So 0.3 was better than 0.2. So go 0.35. That's worse. So I want to get it down. So something like 0.25. Yeah, that's better. So it's somewhere around 0.25 because that figure is smallest. You can play around with this figure to try and find the absolute smallest one. So that's one way of measuring the efficiency of this line. You could use another measure called MAD, the mean absolute deviation. This one takes what's known as the modulus of the number. If you ever covered that in mathematics, it means takes the absolute value. So in this case here it's 110 minus 111, which is minus 1. Forget the minus sign, just forget it. Write down 1. 1 is the difference. So forget that. And the same down here. Just whatever the variations are, just write it down, and it becomes a positive. And the idea here now is to reduce the average. And again, if you vary the alpha here, just press it round, you will find that that number there will change. Okay, so this is how we worked out our exponential set of data, and we think that's probably the best one because we've played around with this figure, this alpha figure, to try and get the smallest average deviation, mean squared error or mean absolute deviation. But what we can do, of course, is we can graph it. I'll take away this graph for a second and we'll do it from scratch just to see what it looks like. So how we would graph it is just highlight those and go to Insert and Scatter. I will take the first one. Let me just move it so it's positioned. Okay, so we've got two series in here. We've got the blue series. This is the original data, and you can see it's scattered around quite a lot. And then we've got the red one, which is the trend that we've calculated. So it's in there. So that looks like a more, it's tighter. This one here it's all over the place. It's looser. What we can do is to figure this one out is we can draw in the trend lines themselves. So let's go here and let's go to trend line. So once you click on this, it brings up an extra layer of tabs. We'll go to layout and then trend line, and we'll go trend line, and we'll have it for the series 1. So that's for the blue one. As you can see, the blue points here, the observations are way off the line. They're down here, here, up here, so they're way off the line. So let's do one for the other one. Trend line, we'll take series 2. That fits closer to the red ones, as you can see. Let's be even more precise. Let's go to more trend line options at the bottom of the list. We'll go series 1, and we'll have the equation and the R squared. And let's move it so you can see it. Let's put it over here, and let's just make it a bit bigger as well. 14 is good. So you can see the R squared here. That's the goodness of fit. It's appalling. It's almost zero. Zero means there is no relationship at all between the data statistically. They're just randomized. If R squared was equal to 1, everything would lie perfectly along the line. That would be an absolute best fit. But 0.06 is terrible. So there's almost no fit in that data. Let's go back here again and go layout, trend line, more options. We'll do series 2. This is the trend one, so we'll do again the equation and the R squared, and let's take it down here. Let's say, yeah, and again, just to make it bigger so you can see it, make it 14. It's the same as the other one. And this time the R squared is 0.72. Well, that's an enormous improvement. So the trend is a far better explanation for the data than the raw data. The raw data is all over the place. It's scattered right throughout, whereas the smoothing data, the trend line is tight. It's 0.72, so it fits the data quite well, which is what we would expect, because we have played around with the alpha here to reduce the average mean squared error. So we have picked the formula that best does this. Right, so that is exponential smoothing. It sounds complicated, but as you can see, it's quite straightforward. And given a set of data, it's easy to work this one out to see which one is best. So that concludes this video. Thank you for watching.